So what we are going to learn in this module is how to test the difference between means of more than two samples. We would also learn about one-way ANOVA and then evaluate problems involving testing for difference in sample means due to one characteristic. We will also learn about which of the means are not similar when other means by two other means, namely the Tuckey's method and least significant difference methods. So students, let me introduce this concept of one-way ANOVA to you. I am sure you would understand that so far we have learned to compare the means of two populations using the test of hypothesis, or more precisely the t-test for the difference between means. For example, if we wish to test the hypothesis that the academic performance of first year students in a college A is equal to or same as the academic performance of first year students in college B, we would set the null hypothesis H0 as average marks of first year students in college A, mu A, is equal to average marks of first year students in college B, denoted as mu B, at some specific level of significance, let's say 5%. So mathematically writing, we would denote H0 null hypothesis as mu A equal to mu B, and alternative hypothesis H0 is denoted as mu A not equal to mu B. But suppose if we have to compare the academic performance of students in more than two colleges, let's say we can easily use the above t-test. We cannot say that. Now, we require another method that can simultaneously test the null hypothesis that the average marks obtained by students of three or more colleges is equal as against the alternative hypothesis that the average marks obtained by the students of these three or more colleges is not same. That means our null hypothesis now would be H0 would be mu A equal to mu B equal to mu C equal to mu D, so on, and H1 is now equal to mu A not equal to mu B, is not equal to mu C, is not equal to mu D, and so on, where now mu C mu D depicts average marks obtained by students of college C, D, and so on. Now in this above case, we can use t-test of difference between means, but we will have to study only two colleges at a time. We cannot take more than two colleges at one time. Likewise, if we wish to compare marks in four colleges A, B, C, D, we will have to perform t-test 6 times, which is 4C2, taking two colleges at a time. The combination of colleges that we will have to study would look like AB, AC, AD, similarly BC, BD, and CD. These are the 6 combinations of A to D, 2 at a time. You would appreciate that when more than two populations are involved, the t-test for difference between means at a specific level of significance, say 5%, becomes a very cumbersome process. If means of 4 samples are to be compared with the null hypothesis that the average marks obtained by the students of 4 colleges is same as at 5% level of significance, then 4C2 with 6 times the t-test has to be conducted. Therefore, we have an alternative in the form of ANOVA called analysis of variance that helps us to test the difference in means of more than two populations at the same time. Since this method examines sample variances to establish whether difference in population means exists, it is known as the analysis of variance method. Let us now look at one-way ANOVA. Let us begin with the concept of one-way ANOVA. The term analysis of variance was coined by Professor R.A. Fisher while studying agricultural data. Here, some selected plots of land were treated with different fertilizers to compare the average crop yields of land after fertilizer treatment. Post-treatment, the difference in crop yield was noted and the causes of variation identified. The variation it was pointed could be caused by assignable causes, and B, it could be the chance causes. The variation due to the first set of causes can be detected and measured, whereas variation due to chance causes is unpredictable and hence not measurable. Variation due to chance causes is called error. So let us consider an example where we wish to compare the impact of three different fertilizers, let's say A, B and C, on crop yield. To study this, we might take a sample of 5 plots of agriculture land where each fertilizer is applied. In this technique, the experimental unit are the plots of land receiving fertilizer treatment, which in our example are 5 into 3 equal to 15. The factor is the variable whose impact on experimental units we wish to study. In our example, fertilizer treatment is the factor, and the 3 types of fertilizers A, B and C are the treatment or factor levels. So our example 1 is crop yield per acre post fertilizer treatment, and we have different columns. We have in the first column experimental units, which are plots of land 1 to 5. Then we have fertilizer A, fertilizer B and fertilizer C, and the output corresponding to each of these plots of land with the use of these fertilizers A, B, C given in these cell values. The ANOVA here consists of a study of variation due to application of different fertilizers A, B and C, and then we divide this variation into assignable causes and chance causes, as we have already explained. Now, what are the assumptions? Are we making any assumptions to the application of this ANOVA? Let us look at some of these conditions which we are imposing. So let us understand the assumptions for the application of this ANOVA. The first assumption is that all populations under consideration are assumed to be normal. The second assumption which we make in this analysis is that the samples chosen are independent. And the third assumption is that the treatment effects or the effects of factors are additive. Let's now look at the model for one-way ANOVA. Suppose we have k treatments or number of factors. So let n1, n2 up to nk denote the number of experimental units or observations, independently drawn samples that are subject to different treatments or factors. For example, N1 samples are subject to treatment 1, N2 samples are samples to treatment 2, and Nk samples are subject to treatment K, such that N1 plus N2 plus Nk or so on up to Nk is equal to capital N, which is nothing but the total number of samples under study. So means for each treatment or factor for the entire population is represented as mu1, mu2, mu-k. Then under one-way ANOVA, the null and alternate hypothesis is elaborated as null hypothesis H0 is written as mu1 equal to mu2 is equal to mu3 and so on up to mu-k, which means means across all k treatments are equal. And our alternative hypothesis now is that not all means are equal. Tabulating the general model, one-way ANOVA table can be written as follows, where we have the treatment or factors and we have sample or experimental units written as 1, 2, 3 so on up to nj, and we have these factors 1, 2, 3 up to k. And these cell values have been denoted as x11, x12 so on up to x1k in the first row, and if you look at the last row of nj, then we have n1 or xn11, xn22 up to xnkk. The sum total of the elements in the first column is equal to t1, t2, t3 so on up to tk, and their means are denoted as x1 bar, x2 bar, x3 bar, x4 bar and so on up to xk bar. Now xij is the result of jth treatment on ith sample. Please observe that n is the number of samples for each treatment. and I is nothing but is equal to 1 to nj, which is samples subject to treatment j. That is, n1 is the number of samples subject to treatment 1, n2 is the number of samples subject to treatment 2, and so on, and our j in this case is 1, 2 up to k, which are our treatments, or in our previous example like fertilizers and so on. Therefore, if you look at x21, it is the result of treatment or factor 1 on sample 2. Similarly, xn3 is the result of treatment 3 on nth sample. That is how these subscripts are interpreted. Therefore, the mean result of jth treatment is equal to xj bar equal to summation of xij, where I varies from 1 to nj, and all of this divided by nj, where nj is equal to number of observations in column j for being subject to jth treatment. Then we can also denote x bar bar, or which is double bar, equal to grand mean of all observations. So what we are doing is we are adding all observations over all the values of I and j, and this can be written as equal to, it is summation, and again in the bracket we have summation of xij. First it is summation of I over 1 to nj, and the outer summation is of over j from 1 to k. All of this numerator divided by summation nj, where j varies from 1 to k, and this is equal to capital N. Please remember, we have already said that the sum total of all nj's is equal to capital N. So here double summation means that we sum all observations within each group, which means treatment, and overall groups, which means samples. So in the above table, we can identify three types of variations. There is variation among all experimental units, which are n in number, n1 plus n2 plus n3 so on up to nk equal to n, as not all these observations are alike. This is called total variation or total sum of the squares, TSS, and this is written to be equal to, TSS is equal to double summation of xij minus x double bar whole square, and the summation is first of I from 1 to nj, and the outer summation is of j1 to k. So total sum of the squares is the sum of the squared deviation of all sample observations from their overall or grand mean. Now there is a variation, which is the second variation among different observations within any given treatment or factor or group, which means within a column. Now this is because not all experimental units subject to similar treatment produce the same result. This is known as within the group variation. It is denoted by SSW, or which means within the group sum of the squares. To calculate this variability, we should sum the variability within all k groups or treatments. That means SSW1 is equal to within the group 1 sum of the squares. How do we calculate this? To calculate this, we take sum of the squares of deviations of observations within group 1, that means subject to treatment 1, from their respective mean, which means from the mean of the first group. So we define SSW equal to summation of xi1 minus x1 bar square, and the summation is of I from 1 to n1. Similarly, you can define SSW2. Now the summation is over of I from 1 to n2, and we have xi2 minus x2 bar whole square, which are the square of the deviations. So we can similarly define these, you may say, within group or within sum of the squares for different treatments ranging from 1 to k or n, whatever we have. In this current example, we have k. If you add all of them, we get SSW, which is total within group variability, and is equal to SSW1 plus SSW2 plus so on up to SSWK. So we can write down SSW equal to double summation again of xij minus xj bar whole square, and the summation ranges from I is from 1 to nj and j ranges from 1 to k. Let us now look at the third kind of variability, which is between groups or treatments. That means experimental units subject to treatment 1 may not have had same impact as experimental units belong to group 2 or subject to treatment 2. Now this is known as between the groups variability, represented as SSB, or sum of the squares between groups. To calculate this, we consider deviations of group means x1 bar, x2 bar, xk bar from the overall or grand mean, which is x double bar. To calculate the total sum of squares between groups, we assign a weight to each group deviation by multiplying it with the number of observations or experimental units in each group. So the highest weight is given to squared deviation of the group or treatment that has the highest number of observations. Kindly note that if the number of observations in each group or treatment is same, that each square deviation gets multiplied by the same number, and therefore mathematically it may not matter much. But therefore mathematically we may define SSB as equal to n1 into x1 bar minus x double bar square plus n2 into x2 bar minus x double bar square, so on up to nk into xk bar minus x double bar square. This can be summarized as equal to summation of nj into xj bar minus x double bar square, where j varies from 1 to k. It can be proved that the sum or the total sum of the squares, which means TSS, is equal to within the group sum of the squares, that is SSW, and between the group sum of the squares SSB. Now it means nothing but that TSS is equal to SSW plus SSB. Let us not forget, students, that our objective is to compare population means for which we study the various sources of variation, which we have defined as within each group and between groups. The variation within a group may be caused by sample or experimental unit, specific factors, and the treatment factor itself will not produce any variation. For example, going back to our example of fertilizers, within a group variation in crop yield may be caused by difference in soil, climate conditions, past plantation patterns of different plots of land subjected to a particular fertilizer, say A, B or C. The fertilizer itself causes no variation as all plots in this group are subjected to the same fertilizer. However, between group variation is caused by some random factors as enumerated above, plus some additional factors like treatment to different fertilizers. Therefore, to study whether a treatment or a factor effect exists, we compare the between the group and within the group variation. So if the between the group variation, which is SSB, is significantly greater than within the group variation, then a treatment effect is said to exist, and the population means are significantly different. In ANOVA, we study the difference between the group variation and within the group variation by using a ratio known as F ratio. The F ratio in ANOVA is the ratio of between the group variation and within the group variation. If treatment effect exists, that means population means are different, then the between the group variation, which is SSB, rises, resulting in higher F ratio. In ANOVA, when we assume equal population variance and set the null hypothesis as H naught equal to mu1 equal to mu2 equal to mu3 and so on up to mu k, then both the within group mean sum of the squares MSW and between the group mean sum of the squares MSB can be shown to be unbiased estimator of population variance. Therefore, for the null hypothesis to be true, MSW is equal to MSB. But if greater is the difference between the two values, greater would be conviction that the null hypothesis of equal variance is not true. The formal test statistics in this case is the F ratio. Now, how do we define this F ratio? F is equal to MSB upon MSW, which follows F distribution with relevant degrees of freedom for the numerator and the denominator. Let's now understand the hypothesis test for one-way analysis of variance. As shown earlier, we set the null and alternative hypothesis as H naught is equal to mu1 equal to mu2 is equal to mu3 so on up to mu k, where it means population means of all treatments are equal, and our alternative hypothesis now I am sure you can also make out will be equal to not all population means are equal. The second thing which we have to understand is alpha, the level of significance, which may be set at 5%, which is generally the case, or at 1% level. The third thing we should know is the test statistic, and we have to get this test statistics. We need to construct the following ANOVA table if we want to understand this test statistic. Now, in this table, we have the source of variation in the first column, which is between groups or treatment, within groups or treatments, and the third is the total. So, we have between groups, within groups, and total variation. Then we have the sum of the squares SS denoted as SSB, SSW, and TSS, and we have the corresponding degrees of freedom as K minus 1, capital N minus K, and N minus 1. And then I am sure you can see in the next column we have the mean sum of the squares, which are SSB divided by K minus 1, could be written as MSB. Similarly, we have SSW divided by N minus K, which is MSW. And in the last column, we have the F ratio, which is written as F equal to MSB upon MSW. Now you can see that we have already defined degrees of freedom, and these have been defined as the total number of observation minus the number of constraints. And these N minus K, K minus 1 and N minus 1 are nothing but the degrees of freedom. When we calculate TSS, then we first need to calculate grand mean X double bar. In the process, we lose 1 degree of freedom, making the total degree of freedom of TSS equal to N minus 1. Similarly, degree of freedom for SSB, which is between the group sum of the squares, where we have K observations, where K is nothing but the number of treatment as X1 bar, X2 bar, Xk bar, then we can see that it can be used to obtain grand mean X double bar. Therefore, the degrees of freedom here is equal to K minus 1. So, let me repeat, what we are doing is we are using X1 bar to Xk bar to find out even a grand mean, and therefore our degrees of freedom is equal to K minus 1. The degrees of freedom for within the group sum of the squares, similarly SSW, you can see from all group observations could be that we have N1, N2 and Nk. From this we subtract group means X1 bar, X2 bar, X3 bar, so on, and then we sum these within the group deviations. Therefore, we find that from all observations N1 to Nk, which is equal to N, we subtract K observations as K mean values have to be first calculated to get the relevant degrees of freedom, and therefore the total degrees of freedom is equal to capital N minus K. Now, what is the decision rule? The calculated value of f or fc, which is equal to msb upon msw, is the one which follows a f distribution with k minus 1 and n minus k degree of freedom in the numerator and denominator respectively. It is the value or its value, you may say, is compared with the table value or the critical value for f with k minus 1 degrees of freedom in the numerator and n minus k degrees of freedom in the denominator, and at a particular level of significance alpha. So we may say and write that if fc is greater than f tabulated, we reject the null hypothesis. Fc is the f calculated value and f table means one which is corresponding to our desired degrees of freedom and alpha. Let's learn one-way ANOVA through an example. So how do we learn this one-way ANOVA? Let's take a question here. Suppose we are given a yield per acre of a variety of crop grown on different plots of land. The plots of land are grouped according to difference in the treatment, that is fertilizer application, A, B and C. The farmer wishes to know whether there is a significant difference in average crop yield of the plots due to difference in the fertilizer. Now, this can be written in a tabular form. We have the crop yield per acre due to, let's say, different treatments. So we have treatment in terms of columns, and in terms of our rows we have the sample of plots. So we have 5 plots for each treatment 1 to 5, and we have fertilizer A, B, C. The cell values, they give us the crop yield per acre due to this use. Now let's find out the solution of this problem. The first step is to fix up the null hypothesis H naught, which in our case now is mu A equal to mu B equal to mu C, which means average crop yield per plot of land with 3 different types of fertilizer application is equal. The alternative hypothesis we have set up is that not all average crop yields are same. The second step is level of significance. We have fixed alpha equal to 5%, and the third thing which we have to do is now find out the F statistic. What is the average crop yield per plot for or after putting fertilizer A? We can find it out, which is denoted as XA bar equal to the sum total of the values in the first column divided by 5, which gives us the average yield equal to 31.6. Similarly, XB bar is equal to 21.4 and XC bar is equal to 23.4, which is again the mean value obtained from the third column. The grand mean X bar is equal to summation Xij divided by n, and this comes out to be 25.47. To calculate the sum of the squares within groups, which is SSW is equal to SSWA plus SSWB plus SSWC. Now we can see that SSWA is equal to summation of Xi1 minus Xa bar square up, and this summation is of I from 1 to n1. Now I am sure we know n1 is equal to 5. So how do we find it out? This you can say the summation of x1i minus 31.6 whole square from 1 to 5. So if I elaborate it further, you can see that this is equal to the first cell value 45 minus 31.6 square plus 40 minus 31.6 square plus 18 minus 31.6 square plus 36 minus 31.6 square plus 19 minus 31.6 square. On summation, you get 613.2. Similarly, we have obtained SSWB, and this comes out to be 147.2, and similarly SSWC comes out to be equal to 399.2 by the similar procedure. Therefore, SSW is equal to 613.2 plus 147.2 plus 399.2, and the sum total is 1159.6. To calculate the sum of the squares between groups, which is SSB, we have done a exercise where we have calculated the summation of nj into xj bar minus x double bar square or whole square, and j is from 1 to 3. Now you can see this on expansion is equal to na into xa bar minus x double bar whole square plus nb into xb bar minus x double bar whole square plus nc into xc bar minus x double bar whole square. On substituting the values and simplification, we get the sum total equal to 292.13. Therefore, TSS is equal to SSW plus SSB and comes out to be equal to 1451.733. Let us now write down our ANOVA table, the required ANOVA table. So we have the between group variation, which is SSB, which is equal to 292.13. We have within group value SSW equal to 1159.6, and we have total variation in the third row or last row where TSS is equal to 1451.73. And you can now see in our next column the degrees of freedom. K minus 1 comes out to be equal to 3 minus 1 equal to 2. N minus k comes out to be 15 minus 3 equal to 12, and n minus 1 comes out to be equal to 15 minus 1 equal to 14. Now in our next column we have calculated MSB, which is equal to SSB upon k minus 1, which is equal to 292.13, which is nothing but the value in the previous cell divided by the value in the next cell, which is 2, and this average comes out to be 146.07. Similarly, we obtain MSW by dividing the value of 1159.6 divided by n minus k, which is equal to 12, and this comes out to be 96.63. In our last column, we have the F value, which is MSB upon MSW. This comes out to be equal to 146.07 upon 96.63 and is equal to 1.512. Let's look at the decision rule. The decision rule now is that the calculated value of f, which is 1.512, is now compared with the table value or the critical f value for k minus 1 and n minus k degrees of freedom, which are 2 and 12 in our example. And the level of significance we are choosing is 5%. Now this value, if obtained from the F table, is equal to 3.89. Now if F calculated is greater than F tabulated, then we reject null hypothesis. Now which is not the case in our current example, because in our current case we find that the calculated value of F is 1.512 and the tabulated value is equal to 3.89. Therefore, we fail to reject the null hypothesis H0. So what is the conclusion? The conclusion is from this decision rule that we conclude that the impact of all the three fertilizers on average crop yield is similar. So let's now learn the limitations of ANOVA and some further tests in this section 4.2. Let's begin with the limitations of ANOVA. ANOVA only tells us whether to accept or reject the null hypothesis for equal means. However, when we reject null hypothesis, ANOVA cannot tell us which of the means are not similar or equal to the others. It is possible to find this using other tests of significance. Now, two such tests are widely used, which are the Tukey's method and the least significant difference methods. Let's take case 1. When there are equal number of experimental units or samples subject to a treatment. In this above situation, like our fertilizer example, we can use both the Tukey's and the LST method. The idea behind both methods is to first calculate a standard value and then compare difference between all means with this standard value. If the difference in means of some pairs is greater than this standard value, it would be regarded that the population means of these two groups is not the same. In Tukey's method, the Tukey value used as a standard value for group-wise comparison is calculated as T is equal to Q as a function of with the subscript alpha k and n minus k into under root of MSW divided by n, where Q is a standardized range distribution with k number of treatments. N minus k is the degree of freedom, alpha is the level of significance, n is the total number of observations or samples, and small n is the number of samples or experimental units in each treatment. The Tukey value calculated above or with the help of this above formula is compared with the absolute value of difference between each pair of sample means. For example, in our fertilizer case, we had 3 treatments, and here 3 pair of groups can be formed for comparing means, namely the means of group A and B, which is nothing but XA bar and XB bar. Then the second is means of group A and C, which is XA bar and XC bar, and the third is means of group B and C, which is XB bar and XC bar. The absolute difference in means of the two groups mentioned in the above 3 cases is compared with the Tukey's value, and if it is greater than the T value, which is the Tukey value, we say that at the chosen level of significance, the population means of the two groups are not equal. In our second method, which is the least significant difference method or LSD method, a LSD value is determined using the particular formula as LSD is defined to be equal to under root of 2 into MSW into F of alpha with 1 and n minus k degrees of freedom and divided by small n, where MSW is nothing but the mean sum of squares within samples, and F alpha 1 and n minus k is equal to the table value for a F distribution with 1 and n minus k degrees of freedom in the numerator and denominator respectively, and at a level of significance denoted by alpha. Small n again is the number of observations in each group, and capital N is the total number of observations, and k is the number of treatments. Once again, we can see that the LSD value calculated by above formula is compared with the absolute difference in means of paired groups. If absolute difference in means of any two groups is greater than LSD value, one can conclude that the population means of the groups in question are significantly different. Having understood this first case, let us now move on to the case number 2. Suppose the number of experimental units or samples in each treatment are different. In the first case we said they are equal, now we are saying suppose they are not equal, they are different. In this above case, only a variant of the LSD method can be used. The LSD math values so calculated for group 1 and 2 is given by LSD 12 equal to under root of within bracket 1 upon n1 plus 1 upon n2 bracket closed into again within bracket MSW and bracket closed into F alpha k minus 1 and n minus k, whereas n1 is equal to number of observations in group 1, n2 is number of observations in group 2, k is the number of treatments, capital N is the total number of observations. Note that LSD value for each pair of groups would be different, as the number of observations per group are different. It is the LSD value of a pair of groups is compared with the absolute difference in means of that pair of groups only. If absolute difference is greater than LSD value, we can conclude that the population means of the two groups are different. That is, if modulus x1 bar minus x2 bar is greater than LSD12, then the population means of group 1 and 2 are significantly different. So what have we learned so far in this module today? We have learned that one-way ANOVA helps to study whether there is difference in means of more than 2 samples. We have also learned to study whether population means are different or not, and this method studies the various sources of variation, namely within the group and between the groups. We have also learned that the test statistics used here is the F ratio, which is the ratio of between the group mean sum of the squares, or MSB, and within the group mean sum of the squares, MSW. The third or another thing which we have learned is that the calculated value of F is compared with critical or tabulated value with relevant degrees of freedom in the numerator and denominator at a particular level of significance. And if calculated F is greater than critical F, we reject the null hypothesis of no difference between means. Once we conclude that there is a significant difference between sample means, Tukey's test and least significant difference method or methods helps us to identify which sample means are not equal.